We were looking at our module 9, and today we will be writing a lot of reactions. Now, if some of you have started looking at your pre-lecture assignment 6, you would have observed that it is nothing but a list of all the chemical reactions that we have covered in this chapter, in this module. Okay, so module 9, primarily there are three kinds of reaction mechanisms that you need to know of. The first is the electrophilic addition reactions, which we do with the binary polar reagents. The second one is the bromination and the chlorinations in presence of a nucleophilic reaction solvent and a non-nucleophilic or aprotic kind of a solvent system. Okay, so we were looking at our alkynes. And we had started also looking at the different ways by which we could make alkynes. Remember, whenever you have to make an alkyne, your substrate should always be a primary kind of a substrate, a methyl kind of a substrate or a primary kind of a substrate. And so your triple bonded acetylide could be anything but the substrate on which you want to attack, because it will follow the SN2 mechanism. You need to make sure there is no bulk on it. Okay. So overall, what will happen if you have this particular substrate, and you are given these two reagents also? Please remember that the sodium amide and acetylene will undergo an acid-base reaction, generating this acetylide. Once this acetylide would be produced, the SN2 mechanism will go on, and we will get our CH3, this carbon right here, with the triple bond, the triple bonded carbon, CH, CH3. Okay, so we had looked up till here yesterday. The last reaction that all of you need to know in this module is the oxidative cleavage of alkynes. Okay, so if you remember yesterday, we had looked at the oxidative cleavage of alkenes. Remember? So we had the double bond, and we have our groups, and in presence of ozone, you will be doing your alkyne cleavage, right? So what do? You just insert oxygens. So from carbon-carbon double bond, you will be generating carbon double bond oxygens. Oh, this is a pentane. Plus carbon with the oxygen, ET, CH3. If you look at these two groups, what kind of a functional group is this? This is a aldehyde. What kind of a functional group is this? This is a ketone. Okay. So from this ozonolysis method, we had looked at the oxidative cleavage of alkenes. How do we do the oxidative cleavage of alkynes? Now, just like we have for our alkenes, we will be cleaving our alkyne also. So right from here. And if you pay attention, I'll put a Z oxygen here. This is what my oxygen is. I will put an oxygen here also. This is what my oxygen is. So looking at this structure, looking at this example that I wanted to show you, what do you have here? Remember your intermediate CH3C double bond O. What happens to the fourth bond? Similarly to this carbon, I'm going to insert my oxygen. So I have the double bonded oxygen with the rest of the group. And so what happens here? Because ozonolysis happens with the acetic acid, you will put a OH here. So instead of being just hanging out, this carbon will have its octet complete. Instead of having a hydrogen, you will have to put a hydroxyl group. Now this was an internal alkyne. What if I had a terminal alkyne? So this is what a terminal alkyne is. Internal alkyne, both carbons of the alkynes have R groups on them. In a terminal alkyne, which is at the end of the chain, you will see a hydrogen on one end and the R group on the other end. So now when I will use my ozonolysis reagents, what would I get? To this carbon, I will get the double bond O with the CH3. And what is the fourth group on this? The OH. What would happen here? Now this carbon will also get oxygen, OH, and H. However, because of certain rearrangements, it will then become carbon dioxide, the highest form of oxidation of a carbon. So remember, that is the only difference. Terminal alkynes, as it's stated here, cleave to form the carboxylic acid and the carbon dioxide. Which carbon contributes? The terminal carbon contributes the carbon dioxide. So for your purpose, what has happened? The number of carbons were 4 here. You have shortened the number of carbons using oxidative cleavage methodology. Any questions? No questions? So all of the reactions that we have seen have been condensed in your book also, and I have posted the same image in these slides where you can see what are all reactions the alkenes can do and what all reactions the alkynes can do. But knowing these reactions is not enough. You need to know what is the mechanism going on in here. Okay, so I'm going to write up a few reactions and we will try to solve for them. And for some of these reactions, I will use the same reagent. Same alkene. So for example, I will use this one starting alkene and I will put different reagents. Each of these arrows will tell you about one kind of a reaction. Okay, so let's do this particular alkene with borane or hydroboration reaction. Sodium hydroxide, peroxide, and then water. So remember, what is the kind of reagent do I have here? And what will it do to my alkene? This reagent, the stereochemistry cannot be very much controlled, but I can control my regio selectivity. It will be anti-Markovnikovs. So where will my OH go? Where will my alcohol go? To the more substituted or to less substituted? To the less substituted. Now remember, when you just see this, think about your stereochemistry also. Both enantiomers will form, this one and this one. And we don't know what is going to happen to this. There is a syn addition. When you do the boration, you will always get the syn addition. Syn addition of what? OH and H. So you know what your stereochemistry of this reaction will be. What if using the same reagent, the same structure, I use mercuration reaction? Now you will need to memorize these reagents so you can identify them also and use them also. Sodium borohydride. Now what is going to happen? Still water will add, OH will add across the double bond. But now I know what is my regiochemistry with mercuration. It is Markovnikovs. What is my stereochemistry? It is anti. So what does that mean for us? This is the more substituted carbon. This is the less substituted carbon. Where will the incoming OH go to? It will go to the more substituted carbon. And this is my hydrogen from the hydride plus enantiomer. Okay, these will just be switched. Any questions so far? What if I had KMnO4 in presence of base and water, and I had cold conditions? What do I mean by cold conditions? I can have minus 78 degrees Celsius. I could have minus 50 degrees Celsius. Anything below the room temperature will be considered cold. So with KMnO4, what do I get? I get diols. Can I control the stereochemistry? I cannot. But can I control the regiochemistry? Yes. Oh, I cannot control the regiochemistry, but we can control the stereochemistry. It will be syn. So both the OH will attack across the double bond from the same side. Plus enantiomer. So you see how different reagents from the same substrate give you different products. But before you draw your product, think about the positioning. Think about the stereochemistry. What would happen if I had osmium NMO, let's say 25 degrees Celsius? Is it cold? Is it hot? No, it's room temperature. What is the product that I'm going to get? I will get a diol across the alkene. Can I control my regioselectivity? No. Can I control my stereoselectivity? Yes. It is also syn. So exactly same product will form. Why both of them do the same thing? Okay, across this double bond, let's say if I have bromine in CCl4. So I'm doing my halogenation with a non-nucleophilic solvent. I am going to control my regioselectivity. It is going to be Markovnikovs. What about my stereoselectivity? It is going to be anti. What does that mean when I say anti? my incoming nucleophilic part and electrophilic part will attack from the same side. I'm sorry, opposite sides. Okay, so this will be trans to each other. This will be trans to each other. The stereochemistry attack is anti each other. And this is more prevalent. The Markovnikov's regiochemistry will be more prevalent when we look at bromine with a nucleophilic solvent. For example, H2O. Now what is going to be my product? I'm going to draw the same major framework. Regiochemistry, Markovnikov's, stereoselectivity, stereochemistry, anti. What is the less or the electrophilic part? My electrophilic part is the bromine here, the halogen here. It will go to the less substituted carbon, and the incoming nucleophilic part will go to the more substituted carbon. That is the Markovnikov's. They are going to be anti to each other. This OH will attack from the opposite direction of the bromine bridge intermediate. Hence, we say it is going to be anti. Any questions so far? No questions? With this reagent, what if I add plain HBr? So these were my halogenation reactions. Now I'm coming to my electrophilic addition reactions. So far, none of these form a carbocation. This is where a carbocation intermediate will form. This is where a bridged intermediate forms. This is also where a bridged intermediate forms in the mercury, in the bromine, and the chlorine, of course, if we had a chlorine here. So this is where your carbocation is going to form, and you can expect rearranged product. What is the regiochemistry? Markovnikov. Because your carbocation forms, you cannot control the stereochemistry. Carbocation is a flat sp2 hybridized molecule. So your electrophilic part will go to the less substituted carbon. Your nucleophilic part will go to the more substituted carbon. That's your Markovnikov. We don't know anything about the stereochemistry. On the other hand, if you had HBr in presence of peroxide, now what is going to happen? Now my regiochemistry will be anti-Markovnikov's. What about my stereochemistry? Cannot control that. So the electrophilic part in this simple reaction went to the less substituted carbon. But this will go right here at the more substituted carbon. And at the less substituted carbon will be your nucleophilic part. Now this is a free radical mechanism. This is not the electrophilic addition reaction on alkene. Okay, this is not that. These are two different mechanisms, different reagents. Presence of this peroxide is going to change the way your product appears or comes out to. Any questions so far? So I'm trying to cover all our different types of questions here. Okay, let's do one more. We just looked at it, the ozonolysis. So ozone in presence of acetic acid or dimethyl sulfide, what is it that is going to happen to this molecule? And let me redraw it here. So whenever I will have an ozone, I'm going to give a break between this alkene. I will put an oxygen here. I will put an oxygen here, and I will open it up. Can I break it from this bond? I cannot break it from this bond. So let me count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. On the 6th carbon, I will have my double bond O. And what else will I have? Will I have a H or will I have a OH? This H is already there, so you don't have to decide that. What about the first carbon? There will be a double bond O on the first carbon also. What else is on your first carbon? A methyl group. So what has happened? From this cyclic ring, it has now opened up. Right? You have oxidized your alkene to make this new material. Any questions so far? No questions at all? Okay. I think I missed one alcohol formation here. So water, acidic water, and then you are going to get a rearranged product. Usually you will get a rearranged product, but here, no control on stereochemistry. No control on anything. It'll be just a carbocation affected structure. We still have 5 more minutes. Let's very quickly. Oh, any questions from anyone on any of these reactions? I'm just trying to write all of these down for us so we can revise them, or you can make flashcards. You must make flashcards. Okay, when we do the synthesis module, I will remind you again on how to make your flashcards. Okay, I will do a few of the reactions with internal alkyne, and then I want to do a few of the reactions with the terminal alkyne also. So one of the prominent reactions will be when you will have excess of HBr or any HCl or HOX, whatever your hydrohalide group will be. How is this going to add on to it? Whichever side you choose, because both of them are equally substituted. Whichever side you choose to add your bromine to, the next bromine will go to the same carbon. Always remember that. Okay, because once you substitute this bromine, it will become di-substituted. This will be mono-substituted. This will become di-substituted. So the incoming nucleophilic part will go to that same carbon, which is more substituted. Excess of bromine or any chlorine also. Now you will completely saturate your triple bond, and you are going to get a tetrahalide. Okay, so the first will be this and this, the next will be this and this. Anti to each other, they will add. Right? What about ozonolysis? Ozonolysis of our this reagent, you are going to get a break from here, CH3, CH2C, CH3, CH2C, and you just put a carboxylic acid here. Then you put CH3C, CH3C, and now you put a carboxylic acid here also. So these are your two products that you will get from this. Another reagents that we had seen, when you do complete, in presence of nickel, platinum, or palladium, when you do complete hydrogenations, at that point, all of your hydrogens will be saturated, but they are add in a syn fashion. The first bond will be saturated by 2 hydrogen on the same side. The second bond, pi bond, will be saturated by the hydrogen atoms from the same side. But what if you wanted to take a break? You don't want to go all the way to the alkane. You want to stop in the intermediate alkene. And that's when you put your P2B catalyst or the Lind-Lars catalyst. Both of these catalysts, whichever you want to use, will give you what? They will give you a cis alkene. Whereas using sodium with ammonia or lithium with any amine or ammonia, RNH2, now you're going to get a trans product. Now we are going to do a little bit with this terminal alkyne. The first thing that I want to show you is the alcohol formation. HgSO4, H2SO4. If water is given, fine. If water is not given, then you assume that there is water here. Where will this OH go? It will go to the more substituted carbon. So regioselectivity is Markovnikov's. So stereoselectivity is syn, stereoselectivity is anti here. So once the enol forms, it is going to rearrange into what? It will rearrange into a ketone. So ketones are formed when you want to hydrolyze your alkynes. You can do that here also. This reaction you can do here also, but you do not see which carbon will be more substituted. So both of these carbons can get the ketone. You can get the 3 keto, you can get the 2 keto as well. Similarly, from this reagent, let's do BH3, THF. Similar reagents, H2O2, hydroxide, and water. What do we get? Now your OH will go to the less substituted carbon. So what is your regioselectivity? Anti-Markovnikov's. So CH3, CH2, CH, double bond, CHOH. So this is another enol. 1, 2, 3, CH3, CH2, CH2, and the aldehyde. So ketone will form here and an aldehyde will form right here. Okay. The last reaction that I want to show you is the ozonolysis reaction with the terminal bond of the alkyne you will break the bond from here, CH3, CH2, C. CH3, CH2, C. You will just give it a carboxylic acid. There is only one carbon with the double bond O and the OH. It will become carbon dioxide. Carbon dioxide is a gas. It is going to go away. So these are all of the reactions that you must know from your alkynes. There are other special reactions that I should have also given you with your alkenes, especially the formation of epoxide. So MCPBA, metachloroperoxybenzoic acid, peroxybenzoic acid, all of them have this particular structure. So what is it that you will see on your epoxide? This is what an epoxide looks like. Further from your epoxide, you can either use acidic conditions or you use basic conditions. When you use acidic conditions, the incoming nucleophile goes to the more substituted carbon. When you use the basic conditions, it follows the steric rules and goes to the less substituted carbon. So your job right now is to memorize all these reagents for sure, and then try to make flashcards. If you can memorize them, then that's perfect. Always think about the regiochemistry and the stereochemistry. And if during the reaction, you will get a rearranged product also. Okay. Any questions? Okay, if no questions are there, we can stop with our lecture today.